Why did I put it here? Okay? Okay, so he puts his money there. Okay, let's see if we can figure this out. So I'm going to do 1, 2, 3, and 4 and see where the signal may be. Who thinks they heard a signal? Nobody? Maybe it's me. Maybe I'm going crazy. I hear chirps all the time. Okay, number 2. Anyone? Okay, number 3. Should I play number 4? Good. Maybe it's just surprise. Maybe I put another one in. Okay, number 3, right? I think everyone agrees. And if you look at it, okay, the signal is there. Right? I'll just click. You can see that tiny little elevation, but it's nothing out of the ordinary. And just like this, you wouldn't be able to tell. And if I now go to the hard case, and again, I'll have someone pick one first. I'll punish the first program. You over there. Yes. Either one of you. Either one of you three. Pick one. Fourth one again. So if the first one was here, the second one was here, where would I put the third one? This one? Okay, let's see if I've actually done this with logic in my mind. I'll start with number 1 first. Can we find it?
Yeah.
Number 1. Okay, so I did distribute it quite well. I even put in a little Easter egg. I went to this. Now let me show you the signal. This is the signal. So if I go back and forth, you can barely see the difference. But our ears are excellent, they are excellent doing Fourier transforms. It's actually a Fourier transform machine. Okay, it's much more efficient than actual machines. And we are excellent match filter algorithms. You'd be surprised. I forgot to put this in. There was a research done by, I believe, researchers in the UK, where you hear a crowded room in a conversation, and of course you wouldn't be able to get a conversation. But if they played a conversation to you before, everyone picks it up. If they don't, nobody understands. Nobody hears anything. You should try it. I can see if I can take it back up. I thought it was a very striking example. And again, it's because we do match filtering every day. Right? We can block off sounds if we're talking to someone. Right? If someone is not listening to my lecture, instead it's talking to someone else, you're actually not hearing what I'm saying. Whereas maybe my volume is higher. Right? So humans can do it, and that's exactly the technique, the match filtering technique that we use, but in an algorithmic way, to find gravitational waves. Anyway, it's just a little interlude so that everyone's awake again. So now we can go back to sleep again.
So do we need to have some people just here with the data?
Okay. You may laugh at this. I thought exactly the same, but I'm maybe a little bit more cruel. I thought we could just buy a lot of dogs. And we would train every single dog to bark at a different waveform. So I would have a template bank of dogs in a room with headphones on and barking when they hear a sound. You may think I'm crazy, it may actually work. I don't think I can get funding for it, but yes, but I actually think it's something that we can do. Now, of course, there are research done that if you listen to white noise for even a few hours, you're completely, go completely crazy. So ethically, it may be very difficult. But yes, you should do it. You should do it. If you can start the grant, I'll sign it any day. Okay, any more questions up to this point? Okay. Now, we still want to quantify things. Right? Before we just listened to it, or we looked at, oh look, this looks nice, and we have seen. But still, we want to do things a little bit more rigorous. And so, first thing that we need to do is define a level of similarity between two waveforms. Okay. So, in this case, what we can do is we can calculate a so-called match. And a match is, I realized I actually didn't put the equation that I wanted to. It's the inner product between one waveform and the other waveform. Simple, noise weight inner product. That's something that Tagoshi has shown. And what we then can do is define the match as something like a geometrical unit. Something that starts with 1 if it's a perfect match. And that then decays away. Now, this is something by now we should all know, right? This is a metric. So if I now define this so-called mismatch, 1 minus m, then I just have a distance. Now why do I define this? Why do I need to define the distance? Because if I want to do mesh filtering, I need to know the waveform in advance. And the question is, which waveforms do I use? Right? I just mentioned I can hire, $100 to do it. Then the funding agency is going to say, why these 100? Why train them on these salaries? Why not use 10? Why can you not use $10? Why do you need $100? And that's this concept, right? Is how close are two waveforms to each other? So we can define a so-called mismatch. Again, this is just the inner product between two waveforms. Okay, so we now have something like this defined, and now we can start calculating, we can approximate this. Right? We can measure this metric, and we can start approximating things. And we can build a so-called template pattern. Because now I know what distance do I need to move in my parameter space in order to be some distance, some real distance away in terms of waveform similarity. So now I can calculate how many dogs do I need. If I show this calculation, I say, okay, we only need 10 dogs. Crap. Government should fund it. Anyone from the funding agency here? Good. So they ask for $100. I can keep some to myself. Okay, so this is an example of two ways in which we can calculate a template value. Now ignore the exact meaning of the x and the y axis. But what we show here on the right is a so-called lattice placement. Right? We place it in a regular grid. The question is, how do you know this grid? Well, that comes from here. If we can somehow figure out, either theoretically or through other forms of measurement, what G looks like, then we can just space them. Right? We know the distance, so we know to calculate, okay, where do I put them so that they are, X far away. And that's what's shown here. This is a very regular lattice placement. And so if G is the correct one, if this is no tilde sign, if this is an exact sign, then this is the optimal placement. Right? It's geometrically, it's exactly the right spacing. But on the left, we see what we typically do. Because we typically don't know this function G, this metric. So instead, we use a so-called stochastic method. And that is, when you run out of all options and pen and paper or your brain just can't solve the problem, what do? You just literally brute force it. So you start with some point in the middle, you throw in another point, you calculate the match. Is it too close? What do you want? You throw in the next one. Is it close enough? It's not close enough. Leave it in. And you just run this until at some point you cannot find any new points. It's very simple. And so this is the way we typically do. Actually, nowadays we're a little bit smarter. We start with something like this, and then we fill it up with this. Because this we can approximate this, and then any gaps we fill in using a stochastic method. But those are the two main methods to which we calculate the template bank. And this is the template bank that we actually use. Now, I don't need to ask you whether this is either a lattice placement or a stochastic placement. This is clearly stochastic. see this in M1, M2, you can see the coverage. Now, one thing that may attract your eye is, one question may come up. Why are there more points here than there are here? Okay? Now, this is the right time to ask you to talk to your neighbor and see if you can, think about, discuss, and come up with an answer why this seems to have fewer templates than places around here. And it's not because, it's not because of anything astrophysical. It's not like we expect more to be here than here. It's a pure data analysis problem. Where we have fewer here, more here. I'll give you 2 minutes. Talk to your neighbor. Discuss. Remember what Tabushi-san said? Right? That the key is there. Anyway, I'll come back in a minute or two. You can also go to the microphone. Let's see. Okay, I don't want to point someone out too hard. People think I may be biased. Any volunteers to give me the answer? Who thinks, oh, I got the answer, right? I'm so smart. I know why. Or I cheated and I looked it up somewhere. It's also good. I did that once. I was in a lecture and my lecturer was asking, oh, does anyone know what this is? And I was like, yes, I know. And I gave him the answer. And he said, oh my God, how do you know? I just took out the book. On my lap, you couldn't see it because it was here. No, it's just me. And he's like, no, even if you can follow it so quickly that you can look it up, it's still good. Right? It means you're already following the process. So don't worry if you looked it up. But does anyone want to give it a go? Don't be shy. There are no wrong answers. But there's a right answer. Anyone? Otherwise I'm going to start pointing. Someone must have come up with something really interesting. Okay, I'm going to bias younger people. Okay? So if you don't want to be, I'm going to start pointing. There's two in the middle. Doesn't help to just look away. I'm pointing at you. Nope, nope, nope. If you look back, then you know it's you. Those two over there. One in green, one in gray. Just stop looking back, it's you.
You don't have any
Yes, you do.
ideas of this thing, maybe
No, the two in front of you. If you're looking back, If you're looking back, it's you.
I think that gravitational wave relation of two big mesh black hole is too complex to build up a data.
Okay, so the answer, what he said was, the bigger the mass, the more complex. But if it's more complex, do you need more or fewer wavelengths? Right, this is heavier. And so by your reasoning, you need more, right? It's more complex. So you'd expect you need more. So I need to train more dogs. Okay, but I have very few dogs here. But still, I like the answer. It's a good answer. Unfortunately, it's not the right one. Anyone else want to give it a try?
Because your different equipment has different sensitivity and different frequency.
Okay, so what she said was different. So your equipment has a sensitivity range,
Yeah.
and also not even just a range, but an actual shape, right? And this determines that shape over there. It's an answer I've never heard before. It's partially correct. So actually, I'd like to give you a little bit of applause.
So the part tensor that is
Right.
distinguish.
Right. But what determines that distinguishability? She said one thing already. So the noise, right? It's a noise weighted inner product. That's what Nagasaki showed you.